Now we are going to focus our attention towards Taylor series and Maclaurin series. First of all, in the previous section, can you remember we kind of used this basic relationship and extracted out power series for different types of functions by doing some little rearrangements or readjustments for this one, as well as we differentiated this function and also we integrated this function in order to obtain the power series expansion of different types of functions. So we did all those things with the basis of this fundamental equation. And this time we forget about this main equation and look for a different path to see whether there are more power series expansions for some other types of functions. For example, fx, right? So from the scratch we are going to find a power series expansion for this function ex, right? And there's one more thing that you should have in mind. When you say power series, there are two main things associated with any given power series, right? One is the center of the power series, and then the other one is the radius of convergence. So when you say power series, you must mention the center of it. Now all these power series that we discussed before are centered at 0, right? And from here onwards we are even going to relax that center and we allow it to be any value. But to start our today's session, let's see whether we have a power series expansion centered at 0 for the function ex. That means we are trying to see whether you can have a power series expansion like this. And if you expand the terms, you will see it like this. Okay, so to begin with, if you write down these terms, then you can realize that this is just a matter of finding the coefficients of these xn terms, right? So if we know the coefficients, so in other words, if we know this an sequence, then we can safely say that we know a power series expansion for the function ex, right? So now our goal should be to find the values of an. But of course, in the previous sections we did not follow this method because we already had this formula. So in order to get the power series expansion of functions like this, we were able to directly use this formula, and for this case, like if we are doing it for this specific case, we can just differentiate the formula, this initial equation, and obtain the power series expansion directly through this one. But for these functions, for more general functions, we don't have a starting place, so we have to begin our discussion from the scratch. Okay, so here we need to find, so like we are trying to find the coefficients at once directly without getting help from any other source, right? But it was not the case when we dealt with these kinds of functions in the previous section, right? Now this is a totally new method that I am going to explain. Okay, so if we have this expansion, now we understood that we should just find the coefficients of an, I mean x to the power n terms. That means we just have to find the an sequence, right? Okay, so to do that, let's see what will happen if we substitute x equals 0 in this equation, right? So when you substitute x equals 0, the left hand side will be equal to e to the power 0, and that is equal to 1. And the right hand side, if you substitute, now say if you have a power series at 0, right? Now this is the power series expansion at 0. The center is 0, right? So now remember, whenever we write a function to be equal to its power series, this equation is only valid within the radius of convergence. So if we substitute a number here, then you will get the same value from the series if that number is within the interval of convergence. Remember, for this one, if you substitute a number like 9, you will get a negative answer here, but you will get a positive answer here, which is, you can clearly see that the two values are not equal. But, the reason for that is 9 is out of the interval of convergence. So you only can substitute the values within the radius of convergence. So how do you know that 0 is in the interval of convergence? Now here you can see that our initial power series has a center 0, right? So always the center term will be within the radius of convergence, I mean within the interval of convergence. Remember, there are three possibilities that it can occur, right? It can only converge at A, it can have an interval, or it can converge on all the values of real numbers. I mean, it can converge throughout the set of real numbers. So these are the possibilities that you can have for the convergence of a power series, and in all these three cases you will have the center value. So it is possible to substitute the center, which is 0 in this case, in both left and the right hand side. Now here we are assuming that you have a power series expansion, right, for a certain r, and we know that 0 is the center, so it is within the interval of convergence. So if it has a power series, then when you substitute 0 to the left hand side, it should give the same value as we substitute in the right hand side, that is for the series. So in the left hand side you have the function, and this is f0, and in the right hand side you have the series expansion. And when you substitute it to the series expansion, you can see that now this is x to the power 0, and that is equal to 1. So this is just a0, and after that you will get a x term attached to each coefficient, right? And it will go like this. So when you substitute to the right hand side x equals 0, all these terms will vanish and you will have only the a0 term, right? So in other words, you can see that a0 is equal to 1. Remember, our goal is to find all these constant values, and now with this substitution we were able to find the a0 value, right? Okay, so a0 is like now we know the value of a0. How about the other values? How are we going to find the remaining coefficients using this equation? Now the method I am going to explain you is a very standard technique. Okay, so you just have to be familiar with that process of finding the coefficients, right? Okay, so what we do here is we differentiate the given equation, right? So this is the given equation, and when you differentiate, the left hand side will stay the same. The derivative of ex is the same. And how about the right hand side? The right hand side, since this is a constant, it will be 0, right? And then here x term will vanish, leaving out a1, and the next term will be 2a2 x, and the other one will be 3a3 x3, and likewise it will continue, and this term will be n times an xn minus 1, and it will continue. Now here I'm sorry, it should be 2, okay, not 3, because when you differentiate this one, it will be 3 times x to the power 2. Okay, now for this derivative term, we can once again do the substitution of the center. So when you substitute the center for this second equation, you will get 1 here because of this one, and all these terms will be equal to 0, and a1 will be equal to 1. So this one will give you a1 is equal to 1. And how about a2? In order to find a2, you will need to differentiate the second equation once again. So let's see what will happen if we proceed it in this way. Likewise, if you continue that pattern of calculating these derivatives and then substituting the center point, which is 0 in this case, you can see that there is a certain relationship that is being emerged, right? And if you do a couple of more steps, you can eventually identify that the general anth term is given by 1 divided by n factorial. And now the other thing is, now here 1 means the derivative of f evaluated at 0, right? So this is the derivative of f at 0, and this is the second derivative. Now this is not the this is a new notation that you should understand clearly. Okay, now this number within a bracket which is being superscript is not the power, right? But it just represent the second derivative. If it is the power, you just write it without a parenthesis, right? But if you have these two brackets and if you have a number inside and all these things are superscripted, then normally that represents the second, that number of derivative. Now here you can write it as f3, right? So this one is f to the power 3 evaluated at 0 divided by 3 factorial, right? Now the actual answer is 6, but I wrote it as 3 factorial, right? And if you do a couple of more steps, you will realize that the general anth term is given by this value, right? N factorial. The nth derivative evaluated at 0 divided by n factorial. So this is a normal pattern that will emerge when you do the calculation, right? So now remember, our main goal was to find these constant values, right? The coefficients of xn terms, right? And through this calculation, we were able to figure out the values of those coefficients, right? And not only that, we were able to even derive a certain specific formula for the nth general term, right? So even just by looking at this formula, you can write down the corresponding coefficient values. So if you do that, then you can see our power series will take this format. So what we have done is, we have obtained a power series expansion for this function centered at 0, right? Now it's very important to mention the center when you have a power series, right? Okay, and there's one more thing that we should do. We should find the radius of this power series. Now the method is exactly the same as we did before, right? We just have to calculate it through the ratio test, and you can see that no matter what x value you have, the limit will be 0 anyway. So that means we can take any x value. In other words, the radius is equal to infinity. And as the final point of this video, I want to summarize this result, basically this relationship, right? So just see what we did here. We obtained a relationship for the nth term, and you can prove that no matter what function you use here, instead of ex, no matter what function you have here, if it has a power series representation, the nth term will be given by this formula, right? So if I state it as a theorem, it will look like this, right? So if you have a power series at any center, now this is generally true for any center, but in our specific example, our center was 0, right? So we evaluated the derivative at 0, but if it is a different center point, let's name it as A, then you just have to evaluate it at that specific center point. Okay, right? So what it says is, for any center point, if the function has a power series, then this Cn, so the only problem we will get is to find the these Cn coefficients, right? So if you can find these Cn coefficients, then that means we have obtained the power series expansion of that specific function, right? And here is the direct formula that you can use to evaluate the coefficients of the required power series. So here you should notice that you have you should evaluate the derivatives at A now, and also you should be familiar with this symbol or the notation, right? This represents the nth derivative, that means nth derivative with respect to x, right? So it's like f is differentiated n times, not the power of n. It's not f to the power n, but it's just the nth derivative of f. And there are some more things that I want to discuss, and I will go through it in the next couple of videos.